Welcome. Previously, I was discussing on labile and inertness. That is, we say that labiles that are the fast reactions and inerts means slow reactions. And what I say is that we are using the two concepts to understand for transition metal complexes, which are inerts and labiles. First one is BBT concepts, and another is crystal field theory concepts. These are the two concepts. We combine these two concepts to classify that for transition metal complexes which are labile and which are inerts. Okay, so he says that for BBT concept he says that D1 and D2 these are labiles. Why? Because for BBT concept to labiles there has to be that there has to present Beckens low line and hybridized orbitals. For CFT concepts that electrons should enter in the edge orbitals. If these two concepts, if these two they have this, if these two conditions if they have, then they are labiles. First one is equivalent to BBT low line unhybridized orbitals should be present. Low line unhybridized Beckens orbitals. Beckens orbitals should be present. And according to CFT crystal field theory, the electrons should enter in EG orbitals, and that is the condition except D8. Okay, so according to this we have classified that which are that labile compounds and which are that inertness compounds. So we have for transition complexes, for transition metal complexes we use either D1, D2, D3, D4 up to 9, D5, D6, D6, D7, D8 and D9. So any of these orbitals will come, so we will classify that which will be inerts and which will be the labiles. So for labiles they has to for here we write let's say labile and here we write let's say the inert. So that these are for labile. Labile means fast reactions they will do. So for labiles what is say that either they should present the vacancy of unhybridized low line unhybridized orbitals. So that will be present for this D1 and D2. So I will write here D1, D2, D1 and D2, and that should be enters in the EG orbitals. So for octahedral complexes I am writing this is for octahedral complexes. So D1, D2, D3 will not enter, so it will come here, and D4 for So D for if it is high spins, then it will comes here. D3 will not comes, means Ag electrons will not enters in the Ag orbital, so D3 will be here. And D4 for low if it is high spins, then they enters into the Ag orbital, so D for high spins, and D5 high spin also electrons will enters in the Ag orbitals. Similarly D6 also enter, and similar D7 high spin also enter. D7 high spins as well as D7 low spins both will be enters in the labile compound. So D7 high spins and D7 low spin also, and D8 and D9 there is no applicable for low spins and high spins. So both D8 D9 electrons will enters in the Ag orbitals, but we see that exceptional for D8 it will be labiles even if it is inerts, even if electrons enters in the Ag orbitals. This will be inerts, then D7 D8 then D9. These are the labiles transition metal complexes. So these orbitals will be there, then we will say that these are the labile compounds. Similarly for inert, then D3 D8, then D4 low spins, that will be not enters in the Ag orbitals. Similarly D5 low spins, and D6 low spins, and then both will be D7 low spins and D7 high spins both will enters in the in the Ag orbitals, so labile. And D9 that is always electrons will enter. There is no concept of low spin and high spins. So these are the labels, and these will gives the inerts. Yes, so if these orbitals are there, then the transition metal complexes are mostly inerts. Okay, so if these orbitals are there, they are classified as inertness, and if these orbitals are there, they are classified as labile compartments. Here that fast reactions happen, and here that slow reactions. So we say that this D1 and D2, this is explained on case of BBT, that low line vacant and hybridized orbitals. And this D3, this is also for that D3, this will not enter in the Ag orbitals. Also we see that from BBT that T3 are fully half filled, so there is no low line unhybridized vacant orbitals for D3. That's why also this is highly inert. Okay, so if these are there, we can check that which are labiles and which are the inerts by looking at the orbitals. Now if that specifically they ask to classify in between labiles which are more labiles, and in between inertness which are more inertness, for that case you have to look this order. Let's say that for labiles, order of labiles. So we see that for order of labiles or order of inertness, what you look first, we look that strong JTD. Strong JTD have are highly labiles. Then come that strong JTD means, it means that which type of compounds that are WT generates degenerate compounds, and for weak GTD complexes are so past we will look that strong GTD, then we will go for that weak GTD, and weak GTDs are triply degenerates. Okay, so first this we have to follow. First strong GTD we look, then weak GTDs. With that we will look also the concepts of BBT. Okay, so from here we will look that order of labels. We look that order of labels. So strong GTD. So for that we have to look that high spins and low spin complexes. So, for order of labels, we have to go two categories. One is high spin complexes. High spin complexes. Another is low spin complexes. For high spin complexes, these are type high spin complexes. Okay, so for high spin complexes, so past that will be that high levels we look for strong JTD. So wherever the strong JTD is there, with that we look also BBT concepts and BBT. Here also BBT. So both these concepts, strong JTD and BBT, and weak JTD and BBT. So for if I look for that high spin complexes, then we see here that labels are D9. Okay, for this D9s there is a this is WG degenerates. So this is highly labels due to JTD, and also if you look at D4, this is also having that W degenerates. So these are W degenerate compounds. This D4s and D9s, because here you see that D4 and D9. This is high spins. So this is 1. So electrons 1, 2, 3, 4. So W degenerates. So this is strong JTD and D9's case 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So W degenerates. So this have the strong JTD. So here we write that first one is D9s and D4. They are equally same, D9 and D4 high spins. This both are having that strong JTDs. So they have the highly labils. Okay, they do strong JTD. Then we will have that weak JTD. So weak JTD, we see that which are the triply degenerates are there. So if you see that D7 high spins and this D2 that BBT concept. So D7s, if you look here, D7s, one, two, three, 4, 5, 6, and 7. So this is triply degenerates. So this D7 and this D2. These are due to weak JTD. They are uh, highly levels after strong JTD. D7s and D2. Okay, similarly, if you go for D7 low spins, if you look D7 low spins, then so this is we are comparing here that order for high spin complexes. Okay, not for low spin complexes. So we will not discuss about low spin complex. Then we go for that D6 high spins. Let's look if any JTD is there. D6 high spins. 1, 2, 3, 4, 5, 6. So here also that JTD is there. So it is not that D7 and D2 with these are also weak JTD, these are high. After that will come that D6 and D1. This is also due to weak JTD. So both have that weak JTD, but for experimental it is found that D7 and D2 these are that high. After that D6 and D1. Okay. After that we will see here. Then what are left? 1, 2, 3, 4, 5, 6, 8, 9. So now after that we have that D5. Also we have that D4. So here after that D5 will comes, then D4. Okay. Then this D3 and D8. So for that inertness, these are the low spins, so we will not took because we are took for this only high spin complexes. So it experimentally found that D3 and D8 are low spin. These are for inertness. Here I not written that low spin or high spin. So these will come both inert low spins and high spins. Okay. Because D for D8 and D9 low spin high spin is not applicable because both the cases the electron configurations will be same. And D3 this is due to BBT, and so it is not that D8 D3 equal to D8 D8 and D3 these are the low spin complexes. Sorry, for inert compounds. So what is found that this up to these compounds they are labile compounds, and the order will be order of labels, means which is more labels, this is the order, and these are inert compounds. And if you compare between D8 D3, then nearly little bit, not too high, D8 is less inerts compared to D3. So that is D8 means D3 is most labile, most inert. Although they are same, but D3 is little bit more inert than D8. So this is the order of labels for high spin complexes. Similarly, for low spin complexes, order of label low spin complexes then that order of label for low spin complexes. So here you see that these are the low spins, or this is low spins, and here low spin high spin will not applicable, so we will take both. In case of the high spin low spin, both the cases D9 we will take, because here that low spin high spin concept will not apply because electron configurations will be same. Okay, similarly these are the inertness compounds. Okay, so for low spin complexes, highly labile compounds are, that is D9. Okay, because this is due to JTD, but here unlike these high spin complexes, D4 low spin will be not labels, and this is component with the inertness, so only D9 is there. Okay, this is due to strong JTD. After that we have labile compounds are labile compounds. After that, for low spin complexes, so we see that D7 low spin, this is also doubly degenerates, sorry, triply degenerates, that is weak JTD is there, so I will write here that D2 and D7, these are due to this D7 is due to weak JTD, and this is comes from BBT, that unhybridized low line unhybridized orbitals. Similarly, I say that this is for weak JTD, this is for BBT, and this is weak JTD, and this is for BBT, this is for BBT. Okay, so D2 and D7. Now after that, this is D7 low spins. So here we are looking for low spin complexes. After that, D1 compounds, and here that D6 low spins are highly inert, so that will not comes. So here we have only D1. D6 will not comes because here D6 was there, here D6 not come because D6 low spin, that is comes into inertness, and it is that fully, let's say if D6 compounds low spins, these electrons are 1 2 3 4 5 6, so this is fully filled and no low lying unhybridized, or sorry, that, so from there we understand that no low lying unhybridized orbitals and they are fully filled. If I say that 1 2 3 4 5, then this amount is 1 2 3 4 5 6, so there are no low, like here D2 sp3 whatever we write that orbitals, so these are fully filled, so no low lying unhybridized orbitals, so this is highly inertness. So here we see that D6 will be highly inert. Okay, compared to D3 D8, also D6 low spin is highly inertness. After that we have D3, and that is nearly equal to D8, these compounds will come. Then we have D4 D5s, so after that D1, then D5 will comes, then D4. Okay, so this is that actual order, and this is, these compounds are D4 D5 D6, D6 and D8, D3. So these compounds are not compounds, and D9, D7, D1, these are labile compounds. These are labile compounds for low-spin complexes. Means here fast reactions and here slow reactions. So in previous class I have made little bit raw data, especially here I put that D4 first, after that D5, but actual order is first D5 then D4. Okay, this you have to remember. First D5 will comes, then D4 for labile. For case of low spin complexes, and in high spin complexes I put again here D4 because D4 I already put here. So in that case I did mistakes, again I put that D4, so that is the wrong. So this is the actual order for labiles, for high spin complexes, and for low spin complexes this is the order. Okay, so labile means they do the fast reactions and inertnes they do the slow reactions. So this is the orders we have to follow while comparing that labile compounds, and while comparing that which is the fast reactions and which is the second reactions. And in kinetic stability what you look that rate. So if that are the labile compounds, then they will do that rate will be high. So here we are discussing about of that kinetic stability. Kinetic stability. Kinetic stability means we will discuss on the rate. Okay, the rate of reactions is high for labile compounds, for labile complexes, and rate of reactions is low for inert complexes. So now we will see that which complexes are labiles and which complexes are inerts. So according to that, that rate is, or if it is the labile complexes, they will be give high rate, and that is fast reactions, and if that complexes are inerts, they will give that slow reactions. Okay, now we will compare that. Other than that, if on what cases that labiles and inerts are depends. If that orbital complexes are this, and if that electron configurations is same, but if there is a difference in charge, or if there is a difference in that is size, then what is that order of labiles? Okay, let's say if we have that chromium 3 plus and we have that vanadium 2 plus. So if you see that chromium 3 plus, that is for chromium the electron configuration is 4s1 3d5. So chromium 3 plus will be that 3d, so 1 here, then 2, this is 3d3. Okay, similarly for vanadium, that is vanadium titanium vanadium, that is 3d2, sorry, vanadium, that is 4s2 3d3, and vanadium 2 plus, that will be 3d3. So both the cases we have that electronic configurations is 3d3, here also 3d3. So according to our rules, what we say that these are that inert compounds, but now if you compare that which is more inerts, then how will you check? So for that we see that inertness is directly proportional to, if inertness directly proportional to charge. So if charge is high, then the compounds are more inerts. and inertness is indirectly proportional to size. Okay, sorry, inertness is directly proportional to size also. This is for transition metal complexes. Transitions metal. For transition metals, inertness is directly proportional to charge, also directly proportional to size. And for non-transition metal complexes, like main group elements, that for that case inertness is directly proportional to charge, but inertness is indirectly proportional to size. Okay, so this you have to remember. For transition metal complexes, inertness is directly proportional to charge, also directly proportional to size. And for transition metal complexes like main group elements, inertness is directly proportional to charge, and that is indirectly proportional to size. Okay, so this is transition metal complexes. So here that it is directly proportional to charge as well as directly proportional to size. So here both the cases that size is same, nearly same, and here difference is charge. So here we look that this is that. So both the case that it is D3. So both are inert. Now we have to compare that which is more inert. On that case, if that electron configurations is same, and we have to, after that we have to compare, then we will look that charge and size. Okay, so if charge is high, then that is more inert. It means Cr3 plus will be more inert than vanadium 2 plus. Okay, so this is the, we can compare that, we will look that charge and size. Similarly, if that is, let's say for if it is non transitions, or we can look another for transition metal complexes. Let's say if it is cobalt 2 plus, 2 plus. So both case we see that this is D7, this is also, this is 3D7, this is 4D7, and this is 5D7. Okay, so for both the case we see that charge is same. Now we will look at size. So for transition metal complexes, that is directly proportional to size. So if size is more, then that is more inert. So this is 3D, this is 4D, and this is 5D. So this is more size. So that inertness is where that iridium will be high. Then both the cases, this is D7, this is D7, this is D7, and charge also same. So now we will look that size. So for inertness, for transition metal complexes, directly proportional to size. So iridium 2 plus, then this 2 plus, then cobalt 2 plus. Okay, this will be the order of inertness. And if you ask about of labiles, then labile is just opposite of inertness, so that will be cobalt 2 plus, then this 2 plus, then this 2 plus. Okay, and here if you ask about of that labile compounds, that vanadium 2 plus will be high, then chromium 3 plus. This is for that labile. Okay, and now if you talk about of non-transition metal complexes, or non-transition metal complexes, that is main group atoms. On that case, what you look that inertness is directly proportional to charge, and this is indirectly proportional to size. So let's say if you take the example of, let's say, magnesium 2 plus, sodium 2 plus, let's say that examples, if I search, that is sodium 2 plus, sodium 2 plus, another is Mg plus. In this case we see that this is a water rich neutral compound, so this is sodium 2 plus, this is calcium 2 plus, and this is Mg2 plus. So here we see that both the case for that non-transition metal complexes, but we will look that how many electrons are there. Okay, so here we see that calciums, magnesium, and scrodiums all are that isoelectronic, all are isoelectronics, so means they have the same atomic numbers. So in this case we will look that size. Okay. So here that what they are indirectly proportional to the size. Okay. So here we see that if I look that size, then size will be that scrodium 2 plus, because down the group size will be increases. If it is that periodic blocks, then what you see that from here to here size decreases, and from here down the group size will be increases. The scrolling is down, so this size is high. So then after that calcium 2 plus will come, then magnesium 2 plus. Okay, this is the size. So inertness is that if size is that is indirectly proportional to the size inertness. So if that is high size, then low inertness. So inertness will be first, magnesium will come, then calcium, then sodium. And for labiles, that is for that directly size is high, then this is just opposite inertness. Labile just opposite of inertness, then that will come that sodium 2 plus, then calcium 2 plus, then magnesium 2 plus. Okay, because this is for inertness, then for labile will be that indirectly proportional to charge, and that is directly proportional to size. So just opposite of inertness is the labile. Okay, similarly another examples I take about of this non-transition metal complexes, then we will look that sodium plus magnesium plus plus. From here if we look that, so these all are that isoelectronic spaces. So now what we look that which is here we see that size is almost comparable because they will lie in that same periods. So now if we look here that charge is different. Okay, so we see that for non-transition metal complexes charge is directly proportional to inertness. Okay, so if high charge then high inertness, so then C will for inertness first C will come, then B will come, then A. And for labiles, that is opposite of inertness, that is A, then B, then C. Okay. Now we will move on to the next topics. Another things, that is substitution reactions. Reactions in square planar complexes is always higher than octahedral complexes. Reason why? Because for square planar complexes we see that there is more space for entry of the new upcoming ligands, and for octahedral complexes there will be less space. If you see here, let's say this is cobalt, here let's say any water is there, this is for that square planar complexes, square planar. And if we look at octahedral, then so here this is coordination number 4 and this is coordination number 6. So here that space is more available. Here also incoming ligands can attack from here, or it can attack from here. Also here is also the vacancy is high compared to this octahedral complexes. So this substitution reactions is very fast in case of square planar complexes compared to that octahedral complexes, due to more rooms or more space available for incoming ligands. Okay, so let's say if it is this rate of substitution reactions. Now we will move to that water exchange reactions. So this is we are going for octahedral complexes. For octahedral complexes, substitution reactions which happen through dissociative mechanisms. So water exchange reaction is one example where that octahedral complexes substitutions happen in dissociative mechanisms. Let's say water exchange reactions. So what have discussed that we have discussed that how that order of transition metal complexes which are fast and which are slow for transition metal complexes and for non-transition metal complexes. So this for water exchange reactions the same things that we will look here also, order of water exchange reactions, where it is fast, where it is slow. So water exchange means what we are doing here. Let's say if this is we are discussing about octahedral complexes. Let's say CO H2O6. Or we look that water exchange reactions in the next class today. After this, thank you.